We're Team 32125, and we're investigating steel strip cleaning methods. We've partnered with Atcor Allied Tube and Conduit, based in Phoenix, Arizona, whose continuous manufacturing process features a caustic strip cleaning section. I'm Amelia Talkington.
I'm Olivia McNally.
And I'm John Totaro, and we are all chemical engineering students at the University of Arizona. Every year, millions of gallons of caustic waste is generated by steel processing plants. This waste is harmful to the environment, poses health risks to operators, and is difficult to reprocess.
For our project, we wanted to investigate environmentally safe and economically reasonable alternatives to this issue. Currently, over $1 million are being spent on supplies annually for the caustic baths being used at Atcor.
The objective of this project is to improve the strip cleaning section of a steel manufacturing line by implementing a more environmentally friendly degreasing method while maintaining industry specs.
Here we can see a video of the current strip cleaning method being used on site at Atcor. It is a series of 4 caustic baths with decreasing sodium hydroxide concentrations.
Here we have a breakdown of the overall continuous process at Atcor. The steel is first unwound by the uncoiler from the spool it arrives on. There's then a welder to connect spools and maintain a continuous process. The strip then passes through an accumulator and then the caustic baths. On this process flow diagram, we have shown our experimental setup with 2 of the CETA measuring devices, which will be discussed later, on either side of the degreasing unit. Then the steel passes through the forming section of the line where it is rolled into tubing and then another welder to secure its shape. The steel then passes through a quench tank, an acid tank, an induction box, and another quench tank before finally being sized, run through another acid tank, and then run through a slitter and packaged.
On this slide, we have tabulated the different steel strip widths and their accompanying line speed specifications. It is important to our design project that the alternative strip cleaning method is able to meet all of these specifications as they are all used for production. When reaching out to companies for more information about the performance potential of some of the alternative methods, we often use 350 feet per minute and 7.85 inches for the steel strip width as the starting off point to gauge compatibility of the new method with Atcor specs, because it would have been the most challenging line speed and strip width combination to meet.
As Olivia discussed, many different strip cleaning methods were considered. However, 4 methods clearly stood out when adhering to our objective statement: steam, dry ice blasting, laser, and induction. Thorough investigations were conducted into each method, and trade studies were performed to determine which method best fulfilled the requirements of our process. For steam cleaning, a steam generating system consisting of a steam generator, nozzle box, condenser, and condensate pump would need to be installed. The nozzle box would consist of 32 jet nozzles, enough to remove surface contaminants from both sides of the steel strip. The force and high temperatures of steam is capable of removing dirt, oil, and rust. Contaminants are heated, lifted, and transported off the steel substrate. Water and steam from the nozzle box can be recovered via condenser and filters and recycled back into the steam generator. Dry ice blasting consists of using high-pressure air to blast the steel with dry ice pellets. As the pellets strike the steel, they sublimate, pulling surface contaminants off the steel strip. The dry ice pellets would need to be produced and stored on-site using industrial coolers and dry ice forming machines. The carbon dioxide produced during this process could then be used to calibrate acid scrubbers further down the line. Laser strip cleaning involves feeding the material in an enclosure containing 4 laser heads, covering both sides of the steel strip. The focus beam of the laser is capable of vaporizing a thin surface layer from the steel substrate. No water or solvents are required for this process. However, adequate ventilation is required to prevent contamination of the laser lenses. In induction heating, surface contaminants are burned off the steel through the use of induction coils. Current is sent through the coil, generating electromagnetic fields that heat the steel strip. No auxiliary systems are required for this process, and precise power settings can be used to dial in the exact amount of energy needed for application, thus optimizing energy use. After researching each method, a comprehensive decision matrix was constructed for method implementation. Here we see an abbreviated compatibility table showing some of the important requirements for our process. Capability to meet line speeds, capability to meet space requirements, installation and accompanied costs, and cost and ease of routine maintenance are some of the criteria of our decision matrix. Each method was assessed, and we found that induction heating best matched all the criteria presented.
Once it was decided which method would be best for implementation, it was time to begin testing its effectiveness on the line. However, before we could begin testing a new method, it was necessary to acquire a device that was able to read the cleanliness of the steel strip as well as determine the baseline cleanliness of the system. After researching many different surface testing devices, our team came across the CETA Cleanospector. It is a device that is able to perform the exact measurements we're looking for. The CETA has an LED element to measure the fluorescence of the steel surface. This fluorescence is able to measure the amount of organic contaminants, which is dirt and oil in the case of our steel strip, in relative fluorescence units, also known as RFUs. Once we had the CETA measurement device, it was time to determine the baseline of the current caustic strip cleaning section. First, since our experiment involved two CETA Cleanospector devices, we had to perform t-test calculations to ensure that both devices had a very strong correlation in the values that they read. A total of 20 measurements were taken with each Cleanospector device, and a t-test analysis was performed. Once it was confirmed that both devices could be used, 25 test points along the width of the strip were measured before the caustic section and after the caustic section. One round of test points used the CETA flat strip measurement head as the steel was still in strip form at this point in the process. The other round of test points used the CETA tube measurement head as the steel strip would be in tube form for the induction readings. Once the baseline data was obtained, it was finally time to obtain the induction data. The caustic system was shut down, and 3 different induction power levels were used to determine the size of the induction box necessary to achieve the cleanliness determined from the baseline testing. The initial power level was the one at which the line was already running, which was 53% of a 1500 kilowatt induction box unit. The line was then stopped and 25 measurements before and after the induction box were taken. Then the power level was decreased to 35% and the line was allowed to run for 30 seconds to a minute after the induction system reached steady state. Then the line was stopped again and 25 measurements were taken again. Finally, the power level was decreased to 15% and the same measurement process was repeated. After all of the data was obtained, the line was allowed to resume regular production operation.
The results of our experiment showed that the induction box, when ran with a maximum power of about half of its full capacity, still removed a higher percentage of waste than the caustic tank. Most interestingly to our project was that the induction box, being set to only 15% of its maximum power, was still able to remove more waste than the current caustic tank system. The lowest power output saw almost 89% removal as opposed to 76% removal by caustic. Now that we have obtained and analyzed our experimental results, we feel confident in the abilities of induction cleaning as a viable alternative to caustic strip cleaning. We would also like to extend a special thanks to our mentor and sponsor company, Thomas Babb and Atcor Allied Tube and Conduit, as well as John Kane and Fletcher O'Connor, the technical support team from CETA, and lastly, Dr. Kim Ogden and Dr. Adriana Brush and the rest of the chemical engineering department at the University of Arizona.